So today we are going to tell the story of Spectre and Meltdown, and this is quite a curious thing because some people asked us, is this a conspiracy theory? So this vulnerability existed for many, many years, and still no one discovered it before just now. And suddenly, 4 independent teams find it within 6 months of each other. So maybe we should start, as in every crime TV series, with an evidence board.
Exactly. So we did that as they all do in the television shows. We start with an evidence board. So in the middle we see what we want to solve, the mysterious case of Meltdown and Spectre. So what is our first part of the evidence? It's the team from Graz University of Technology, which includes us, and so Stefan Mangard, Michael Schwarz, Moritz Lipp, and Daniel Gruss. This is our first part of the evidence that they are somehow connected to this Meltdown and Spectre vulnerability. And who else do we have? So another person here, it's Anders Fogg, and he must be somehow connected to us. So who is Anders? Is he an academic? Is he a hacker? What has he to do with all that?
Maybe I can contribute something here. Actually, I shared a room with Anders at BlueHat 2016 in the USA. So there we also talked about something that was related to Meltdown, but I told him, yeah, that's not a good idea. Probably it won't work because I come from an operating systems development background, and for me it was clear that it can't work.
And so we read his blog about his experiments of trying to read kernel memory, so there must be some connection here. And maybe there's more connections to Anders, right?
Yes, actually we published a paper together with him at CCS 2016 about the prefetch side channel attacks with which we de-randomized the kernel address space layout. And also, I think you also had a connection to him.
Yeah, as you said, BlueHat, I also remember sharing a room with Anders at BlueHat Europe.
So you too?
So
That's
in
weird.
2016, that's really weird. So. Really weird, so definitely somehow connected. So yeah, after talking a lot with Anders and reading his blog, we decided to try, maybe there's something with Anders' ideas. Anders is a genius, he has always great ideas, so maybe he's also right here, although he was not sure himself. And that's when we discovered Meltdown in December. So what did we do next? What was our next step? Of course, as responsible researchers, we contacted Intel. So Intel is also part of our evidence board here. And then from Intel gave us more pointers to other research teams. So suddenly there are a lot of more people involved in that. So we have from Germany the Cyber Technology team with Werner Haas and Thomas Brescher, a startup in Germany, and they also read Anders' blog and thought, maybe this could actually work. So they have quite a good background in the low-level stuff. So we decided, maybe there's really something behind that. And then we were connected to Google, the Project Zero, here with Jan Horn, who also discovered Spectre and Meltdown. And the fourth team was the team around Paul Kocher with Daniel Genkin and Yuval Yarom, and Paul, the famous cryptographer, and also not a coincidence here, right, Daniel?
Actually, Paul Kocher described cache timing attacks as far back as 1996. So he was one of the first who described these attacks. So this is not a coincidence, it seems.
And also, when we discovered he was working with Daniel and Yuval, there's something else, right?
Yes, that was pretty interesting because actually we were currently collaborating with Daniel Genkin and Yuval Yarom on a current Rowhammer publication, so a new Rowhammer attack. So this was also very interesting that there's this connection.
But that started with Yuval, right?
Yes, and there was another thing that there. Actually, Yuval Yarom was in Graz when he was one of the examiners for my PhD proposal. So we have quite some connections there.
But is Yuval is more connected? Is Yuval connected to anyone else?
Actually, I heard that Yuval and Anders met in 2016, but I don't know what they talked about in this meeting.
It was a kind of a secret meeting. But that's not all. We have another connection to make this net more dense. So actually, in 2017 at a conference, there were Stefan Mangard from our team and Yuval, Yaom, Daniel Genkin, and Paul Kocher, and they all sat on the same table discussing whether performance optimization might have security impacts. So already back then, they were together and talked about stuff that ultimately led to Spectre and Meltdown. And
actually, there's another connection. So I know Jan Horn since 2015 from online discussions when I presented page deduplication attacks in JavaScript, and Jan Horn was very interested in those, and I tried to get him to Graz so that he does his master at TU Graz, but I couldn't convince him. Yeah. Very sad for us.
So if we look at all those connections, it doesn't look like a conspiracy at all. Because the tools that we use to detect and exploit the bug were only discovered by Yuval Yarom with Flush and Reload in 2014. In addition, there was no real broad interest in micro-actual attacks before, and the discovering teams were quite knowledgeable about those attacks. So besides our team and the ones who worked on that, also the guys from Amsterdam, VUSEC, and also the team around Thomas Eisenbart work intensely on micro-actual attacks, so there are not many people working in this field. So in the end, as we can see, the bug was ripe. So we had all the tools and all the necessary background to find this bug and really discover it and look at the consequences that it brings. So a collision with all those people was nearly inevitable. But in the end, if we look at the bug, you only know it's really big when in the end you have news about it all around the world. So Fox News reported it on television, also CNN, that billions of devices are affected, that the names Spectre and Meltdown came across in different shows, so there must be something about it in the end. And also on the stock market, you could see that the values dropped slowly.
So there's another thing, another indicator that you know that it's something big. When you get a Wikipedia article, of course, that was also something that we were very surprised to see. We have a Wikipedia page for Meltdown and one for Spectre, and yeah, quite big. And we're
and you even know it's really interesting for a lot of people if you even get your own comics about you, even on XKCD or on Commit Strip, and they try to explain the certain stuff in a funny way here. And also when even the mass media and Snowden mentions you in his Twitter posts, and then you get a lot of followers after Snowden takes your video, and some people accuse you of stealing the demo video from Snowden.
Okay. Before we start with the actual Meltdown and Spectre attacks, we should first start with the basics, and the basics are operating system design. And here we have some isolation between the user space and the kernel, and this is usually, you can imagine it like a huge big wall. It's a huge wall between the protected safe part, that is the kernel, and the untrusted part, the chaotic part, the user space. And this one isn't working.
Okay.
And if we look at the video here, you can see the wall illustrated, and you can see here a syscall which goes slowly and carefully with a small payload over this wall. And so it's a very controlled and defined interface here.
So we found this nice kernel documentary that explains a lot of operating system basics here.
Okay, yes, then maybe we continue. If we take a more technical look on this, then we see that this wall, yeah, it looks a bit different maybe in the processor, but basically it's software configured, but it's hardware backed. It's a combination of hardware and software features to isolate user space from kernel space. And you can see all the apps on the user space half, the calendar app, the photo app. And these apps can't access all the memory that is mapped in the kernel space. They can't access the tasks running in the kernel space. And so this is somehow protected. As we have seen in the previous kernel documentary, there is only this defined interface, the system calls, or short, syscalls. So
let's continue with the kernel documentary. As said before, we have this huge wall here separating the kernel space from the user space, and you can see it's massive. You cannot breathe. Whoa.
Okay, maybe we should go a step further back. Before we think about how this exploit works, maybe we should think about cooking. Because cooking, there are some analogies that work quite well. And when cooking, maybe you have all the things already prepared, sitting on the table, and then you realize, oh no, actually I have one ingredient which is missing. And what do you have to do when you have one ingredient missing? You actually have to go to the grocery store. And that takes some time. And this is quite bad if you have already guests arriving in an hour, and then you have to go to the grocery store, and then you go back, and then you realize, oh no, there's something else missing, and you have to go to the grocery store again. And so you get more and more latency because you have to go to the grocery store all the time for every single ingredient. Really annoying. But I invented something with which we can avoid that.
Really?
Yes. I call it the food cache.
It's a fridge, right?
No, it's not a fridge, it's a food cache. Something like this hasn't existed before.
Okay.
You can store things from a grocery store in this food cache, and then you have them ready to use when you need them.
But that's amazing. That's revolutionary. That's
yes.
a really,
wait a minute.
concept.
That's nothing new at all. We have this for years in our CPUs. So we have the CPU cache. And what it does, when you have an address and you want to load it, it will first take a look if it's in your food cache, so in our CPU cache. If it's not there, we have a cache miss. Then we have to go to the DRAM, ask for the value.
So the DRAM is the grocery store.
Exactly.
And the CPU cache is the food cache.
Perfect.
Huh.
So we load the value from main memory. We get a response, which is automatically stored in the cache, and we have it in the cache ready for further use.
So then I don't have to go to a food cache anymore.
Yes. So the second time you want the address, you have a cache hit because it's already in the cache. So it's quite fast if you load it. So if you have to access the DRAM, it's very slow. But if it's already in the cache and you do not have to access the DRAM, it's much faster. And you can measure that. And based on that properties, Yuval Yarom suggested the flush and reload attack that we also use for Meltdown and Spectre.
Wait a moment, Yuval Yarom was the guy we had on the evidence board, right?
Correct.
What a coincidence.
So imagine an attacker process and a victim process. And they use some shared memory, like a shared library. And if both of them have those shared library, if one of these addresses is cached, it's cached for both of them. So the attacker can now go there and use the flush instruction to throw stuff out of the cache, like when you throw something out of your fridge. So it's not there anymore. And then, when the attacker is scheduled, he will access the location again, which will load the address back into the cache, and it's cached again. And now the attacker can go and measure the time it takes to load the address. And as we've seen earlier, if the access is fast, the victim has accessed the cache. So the attacker knows exactly when the victim has accessed the cache, and he can do that over and over again to spy on the victim.
Okay, but now enough about this computer stuff. Let's get back to cooking. And I have another revolutionary concept here that I want to present.
Oh, really?
Yes. Actually, it's something that happens every time to me when I cook something. I go through the recipe, and I've done all the steps, and then in the end there's a point, serve with cooked and peeled potatoes. And you know where the potatoes are. They are sitting right there, not peeled, not cooked. And now I have this additional delay, but the guests are arriving. And this is terrible. This is latency, and we want to avoid latency when cooking, right? And for this purpose, I've come up with a pretty clever idea, and I call it out-of-order cooking. And here, I first go through the recipe and read ahead. I read ahead of the step that I actually should do.
So you don't do the steps step by step?
No. I check them.
But it's not supposed to be not step by step.
Yes, but it still works most of the time. And so you can parallelize the different steps here as long as they don't have any dependency. And this is a revolutionary new idea how you go through recipes. And then you have the meal ready in time.
Yeah. So really in fact, this revolutionary idea we have for 20 years in our CPUs, of course. So if you have some code, then what the CPU can do is everything that has no dependency, it can run in parallel. So it's much faster. So only in the end, when we need all those values of those 4 variables, we need to wait until all the 3 steps finishes, but all those 3 steps can be computed in parallel. So there's nothing new.
Okay, so let's go back to this documentary. So we had the huge wall before, and now we will demonstrate what Meltdown actually does. So, it's dark. So here we can see Meltdown. No, we can't see it. And this is Meltdown using the actual vulnerability to destroy the wall. And we can see the wall is breaking apart and falling down. And here we see Meltdown is going away now.
And now basically any user program can access anything of the
So the isolation is completely gone, and the user process destroyed this wall and can access everything that's in the kernel that should be inaccessible.
That looks pretty easy, right? So we just implement that. So
how do we do that?
We need a kernel address. So we just grab for the Linux banner in colsims, then we have the address.
So we have this address, and I know that from programming 101. I just take the address, make it to a pointer, and dereference it, right? And then I get the value.
Yes. Sounds good.
Like that, yeah.
That won't work.
Easy.
That won't work. I taught programming for quite a few years. If you write that code down, your program will just crash, right?
Why?
See, I told you.
Oh,
God damn it.
Why is that? Can you explain why this does not work?
Because you cannot access this address from user space. You have this wall, and you cannot just run through the wall. Try to run through a wall. It doesn't work.
If I try hard enough, maybe.
So kernel addresses are, of course, not accessible. And when you try to access them, you will get a segmentation fault or a page fault.
Okay, so it's not that easy.
No, but as we all know, if you have an exception, you just have a try and catch block and you're done and the error is gone, right? So we just catch the segmentation fault. That's easy. So we can just simply install a signal handler if we use C. And if an exception occurs, we just jump back to the code and continue our attack.
Oh, that sounds like a really cool idea.
Yeah, then we can just read the value.
Yeah, just catch the exception. Okay,
have you tried that?
Sure.
What happens?
Sounds good. Okay.
God damn it.
Maybe it was not your brightest idea. We still don't get any kernel memory here, so...
I told you so, right?
So maybe it's not that straightforward. And maybe these privilege checks, they actually seem to work really reliably. So maybe the hardware is really good and there are no vulnerabilities there. But I have an idea. So maybe if we execute stuff out of order, as you've told me before, maybe the privilege checks are not done there correctly because the privilege check can be parallelized and then it's too late for the privilege check.
Okay, let's look at this example here. So what did you do there?
I tried that here. So I have a null pointer dereference here.
Your program will crash when you do that, right?
Yeah, that's okay. So I expect it to never continue after the null pointer because it will crash, sure.
Okay.
And then I access some data here, an array.
What do you expect that to do?
I expected that if it's executed out of order, then it will be cached because it will be accessed. There's no dependency here.
And then you can observe it through the flush and reload attack?
Yes, exactly.
Okay, but your compiler will stop you here.
Oh, no. I just added a volatile here because the compiler was not happy with my code, told me it has no effect. I'm not sure that's actually the case here. I think it has an effect. So I added the volatile. And I mean, my static code analyzer was still not happy. It says you're dereferencing a null pointer. But I'm pretty confident that it works.
Yeah, so if we have out-of-order execution and we have those instructions running out of order, despite the fact that we are dereferencing a null pointer, what can happen is that data is still loaded into the cache and leave measurable traces in the end. But it will raise an exception, right?
Yeah, but it's already in the cache. So even though it's aborted, the memory is cached here. So that's something. So
Okay, so if we try to structure that in a way, we know that out-of-order instructions leave microarchitectural traces, and maybe we should give that a name. So we can see these microarchitectural traces, for instance, in the cache, but there are also other mechanisms that we could see, and to generalize this, to give this a name, we call this transient instructions. And transient instructions are instructions that leave microarchitectural traces, although they are never architecturally executed. And we can indirectly then see the effects of those transient instructions.
okay. So maybe for these transient instructions, there's actually no permission check.
But maybe it just occurs whenever the instructions are finally committed.
Right, so maybe we have a time window where we can work around this permission check here. So I have another piece of code here. It's again quite simple. So I thought maybe add another layer of abstraction of indirection, as we always do in computer science, solves a lot of problems. So I take the kernel address here I want to read, and I don't try to read it directly, but I use it as an index to an array, to a memory location, and then I expect that a part of the array is cached afterwards, because it's somehow executed in transient mode, out of order, and then I just check which part of the array is cached, and I know what the actual value was that I read from the kernel address.
So when you actually do that, and then you run flush and reload over all the pages, you actually find that the flush and reload attack will have a negative spike at the exact index where you accessed the memory, the array.
So we can actually see the data here.
Yes, you can directly reveal the information. The permission check apparently is not fast enough in all cases.
So in this
what can we
case,
do with this?
I just read one character here, but we can do that in a loop, for example, and then read multiple characters, such as passwords. So I use this code on the address of this password field, and when someone enters their password, I can just read it using this transient instruction sequence here. And I get the password.
This looks bad.
Okay. Actually, when seeing this, it looks so much like in these CSI cyber shows. Do you know these CSI cyber shows? There's this
Reflection in your eye. Let's run this through video enhancement.
Edgar, can you enhance this?
Hang on. Can you enhance the image from here?
Can you enhance him right here?
Can you enhance it?
Can you enhance it?
Can we enhance this?
Can you enhance it?
Hold on a second, I'll enhance.
Well, we will check whether we can actually enhance it with the Meltdown attack, and actually we can. So this was, all the time we thought this is technically not accurate, but actually it might be.
They were just ahead of their time in television.
Okay.
Perfect.
All of today's events, it's Evening News with Tom Muslicker.
Terror, crisis, and fear tonight. Meltdown has shattered the belief in computer systems. We are all doomed.
So, not so fast. So, we can read arbitrary memory, we can read passwords, and we can reconstruct images like in television. But we know kernel addresses in user space are a problem, so we can easily fix that, right? So, why don't we just take all the kernel addresses and remove them? Sounds easy, right? Because user accessible checks in hardware are not reliable. So we just unmap the entire kernel in user space, as we've seen on the images before. And then all those kernel addresses, and also the identity mapping with the addresses of the entire physical memory, are not present anymore. And memory, which is not present, cannot be accessed at all. So we're done. We fixed Meltdown.
So actually, this is what we proposed in our Kaiser paper, and Kaiser stands for Kernel Address Isolation to have side channels efficiently removed. And Kaiser, the word, comes from German emperor, ruler of an empire, but also second meaning the largest penguin, the emperor penguin.
So this is good for Linux.
Yes. Just
So,
coincidence.
To illustrate that, as we've seen on the image before, on the left-hand side we have the user space applications, the wall, and on the right side the kernel space with the kernel and the operating system. So what we do now is when we have a context switch, we just unmap the kernel for the user view, and in the kernel view everything is still fine, but just not accessible.
So that's really cool. So if the user tears down the wall,
Yeah,
with the
there's
Meltdown
nothing
exploit,
behind it.
There's nothing.
So he
Perfect.
can't read anything anymore. So, as said, we published this in July 2017 as a countermeasure against different side channel attacks to defeat KSLR. And Intel and others improved and merged our proof of concept batch, now named as KPTI, into the Linux kernel. Microsoft also implemented that in Windows 10, and Apple also implemented that in Mac OS in 10.13.2. So at this point, we want to thank all the developers who spent probably endless hours into fixing our operating systems
And all-nighters, I guess,
Yes.
to have that ready.
in the last few months. So thank you for that. But in the end, even if those patches are called differently now, depending on the operating system, so Apple calls it double map, they all share the same idea, that we switch the address space on a context switch.
So wait a minute. That means we have two address spaces and we have to switch all the time and have things duplicated. So that sounds really, really slow.
Daniel.
Yeah, actually, it can be really slow. It actually depends a bit on the hardware and your specific use cases. It depends on how often you switch to the kernel and back to the user space. So if you have something like searching for files, many small different files, then it might be really slow. But if you have workloads which are mostly in the user space, then it might be really, might not really make a difference. So it can be really slow. 40% or more on old hardware. There was some engineer from Amazon who basically this one caught our attention when we were investigating this, and he posted that they had 400% overhead on one specific benchmark test. And then we thought, okay, this is a bit weird. If Amazon is going to accept 400% overhead, we should see what is going on. More modern CPUs have additional features. For instance, we believe that they do some more clever stuff in the TLBs. Also, there's the PCID feature, and with these features, it becomes a lot better performance. Then the performance overhead may be as low as 2% on average for usual workloads, not if you have something which is very file intense. So
for Meltdown, we have a fix, we have Kaiser, and whatever names it's called in addition. So we don't have to care really about it anymore if everyone patches their systems. But how about Spectre?
Okay, so we still have the case of Spectre, and I like to go back to explain it in a cooking kind of way. So we at the university with our favorite pizza place where they have the best pizza there, and so we go there quite often. And if we are there, we are usually 6 people, and then we order pizza, and it's like always kind of the same thing, so we order the same things, and we have a prosciutto and a fungi, and then we have 4 diavolos, and that's the usual thing. And because this pizza place is so good, we have to usually book a table in advance. So we call there and we say, yeah, it's university here, we'd like a table for 6, please. And then they know we are coming, and what they also know is, okay, it's the same guys, and they order usually a lot of Diavolo pizzas there. So let's prepare at least 3 of them, because they order always at least 3. We don't know about the others, but that should be a safe bet to do that. So that's kind of speculative cooking. So they do that in advance, and when we go there, the Diavolo is always the fastest pizza, so we get that right when we come there, and the others have to wait a bit. So everyone is happy. And now, maybe there's a different university that likes to know what we usually eat at the pizza place. So what they do is they also say, call there and say, university here, table for 6, please. And although they are different guys. And then the pizza guy knows, oh, the university is coming, let's do our speculative cooking, make the diavolos there. And then suddenly, someone else is coming, it's not us. And the pizza guy is like, oh, damn it, wrong guy tried to spy on what the university people are eating, so he throws away the pizzas.
But in the end, the smell of the pizza remains, and the attacker knows what you're eating.
Oh no.
And this brings us to speculative execution that we have in our computers for so many years now. So if we look at this simple application with one data string, an index, and a bounce check, which checks if the accessed index is below 4, what happens is that when you try to read the first character, you go there, you come to the branch. Doesn't it work? Can we check? Okay, and the CPU speculatively thinks, okay, what can I do next, because I have nothing to do. Maybe it will speculate that you go to the else branch and does nothing. And when it finally evaluates the real index, it will know, okay, I have to take the then branch. And as we can see in the middle, we train the prediction unit to improve further execution. So we go to the then branch. So for the next character, we also have slightly trained the prediction unit already. When we try to access it, the CPU maybe speculates already that it should take the then branch. It can compute the value in advance. And after it evaluates the if condition, it will know, okay, I was correct. Now I'm pretty fast, and I can do this for the next characters. And now the CPU speculatively executes the correct branch because we trained it to do so. And we get pretty fast, and our predictions are almost all the time correct. But what happens if we now try to access the 5th character? So we would fail the out-of-bounds check. But we already trained our prediction unit to speculatively execute the then branch, and now it will take the value, the k value, which is secret and should not be accessed, and uses it to access some data which we then can monitor with the flush and reload attack, as we've seen in the Meltdown attack. But then it will figure out, okay, I was wrong, I just throw away the results, but we still have the traces in the cache, so we still know what value has been written there, and the CPU knows, okay, the bounce check was wrong, I should have taken the else branch, throw everything away, and continue there. And as we can see, we slightly untrain the prediction unit. Also, for the following characters, the principle is the same. It speculatively executes the code it should not execute and will untrain everything.
Okay. There is a second variant of Spectre, and in this variant, we are targeting the so-called branch target buffer. And the branch target buffer basically provides us with a prediction where a branch, an indirect branch, will go to. And I thought of a very simple example, and a very simple example is this C++ code where we have a base class animal, and we have different specific classes of the base class animal, for instance, bird and fish, and they have different methods, different instantiations for the move method. And you can see the one method does some operation based on the data, the other maybe does not do the operation, but imagine that the index here is some member variable of the object that is just used in this code speculatively. And now if we start here, maybe we start with bird, and then we go to the swim method, because maybe this was previously called the last time we were there, so we speculate there. The next time we go there, so this one executes now, and with that it updates the branch target buffer, and the next time we go there, it will predict the fly method. So if we call this again, the move method again, it will now predict the fly method. And That's fine because this works on the data that we intend to use here. But when we now switch the animal pointer A, if we switch this object, if we point to a fish now and call the same method again, we will, of course, speculate here and have the leakage, which, again, allows us to read probably arbitrary data from the kernel or from the other process context. Yes, and then the other one is executed again, and the prediction is again trained in the other direction. So this is basically almost more simple in a way than the other attack, because it's more direct in this example. But there are also more complicated examples where you try to train this prediction through some indirections, through some collision of the branch target buffer. Okay, that's, yes. How do we use Spectre? So both variants of Spectre, Spectre 1 and Spectre 2, can be used in similar ways. It just depends on which code gadgets you have in the other process. And they allow to read your own memory. If you're, for instance, running in a sandbox, in JavaScript, for instance, you can use that to read memory that you're not supposed to read. But you can also convince other programs to reveal their secrets. So you're basically hypnotizing the other programs, or basically, most of you know the Jedi mind trick. So you're convincing the other program that they reveal their secrets to you. And then again, we use a cache attack to obtain the secret. This one is much harder to fix because in the other case, we said we want to stop someone from accessing someone where he's not allowed to access, right? But here, we cannot really stop another program from voluntarily revealing the secrets, right? The other program does that to some extent voluntarily.
More or less, yeah. So can you fix that?
Actually, there's ongoing effort to patch this via microcode updates and via compiler extensions.
So Moritz, can you tell us more about that?
Yeah, so we need the Ghostbusters to kill the ghost in the end. So for the first variant, we have the L-fence instruction.
Did you just say elephants?
No, I said L-fence, like load fence, like a memory barrier. And what it does, it is a barrier in the end to serialize all the loads from memory. So no further speculation is done, and we just insert this after every bounce check. So we can implement this as a compiler extensions, and at those places where we need to do this, we just have this barrier, and we are fine in the end.
For variant 2, there are also mitigations. For instance, Intel calls it the indirect branch restricted speculation, which is basically a mode that the CPU can enter, and when entering this, it won't speculate based on anything that was computed before entering the IBRS mode. The question here is, what if we have a hyperthread running simultaneously on the same CPU core, which again trains the branch target buffer, for instance? Then maybe this doesn't work. Another option would be the indirect branch predictor barrier. Basically, we have some MSR where we can write to flush the branch target buffer. But again, what if we have hyperthreading? We can still mistrain the branch predictor. And there's a third variant. Intel calls this one the single-thread indirect branch predictors. And this is commonly referred to as red polines. Red polines look like this. So,
wait. Are you telling me you replace every indirect jump by this construct here?
Well, yes.
Okay, and this that works in terms of performance?
Yeah. So basically, this one will always predict to enter the endless loop here in around the go-to target 2. And as it always will mispredict, it will never predict to go to the correct or wrong target function. So yeah, we will always have mispredictions here.
So the performance is maybe not as fast as
it depends on
now.
If you avoid indirect branches, you don't have a performance loss.
Perfect. So if I don't use it, it doesn't cost performance.
Also, we have a problem here on Broadwell or newer CPUs. Their return might fall back on the branch target buffer for prediction, and then there are microcode patches to prevent that again, but again, probably this, again, costs some performance. What do we learn from it? So basically, we can say we've been researching attacks in this area for many, many years. And we as a community have ignored software side channels for many years. We have seen attacks on crypto.
Yeah.
Yeah, but we can fix it in software, just implement the crypto right.
Well, what about the attacks on ASLR?
It's broken anyway.
But the attacks on SGX and trust zones, what about them?
Out of scope,
Okay.
not in our threat model.
So for years, we solely optimized for performance. And that's something we do not do in other areas. In other areas, we do not optimize for performance only, but also for other targets.
So after learning about a side channel, you always realize afterwards the side channels was documented in the Intel manual. So it's not something that's surprising. Just no one understood the implications of the side channel before. So for the speculative execution, it was always documented in the Intel manual that it might leave traces in the cache. But we didn't get the security implications of that.
Despite in the automotive industry, if we look back 100 years when cars were invented, we had many deaths per year where people died because we didn't optimize for safety in the end. So we didn't have seat belts in the beginning, we didn't have airbags, we didn't have ABS, but with introducing that, we improved and improved for safety. And in contrast to CPUs, where we just... Oh, it's loud. where we optimize for performance all the time. Our cars don't get necessarily faster every year, like it's not 500 kilometers
But they get safer.
But they get safer, exactly.
So now we have a unique chance to rethink the processor design. So this is this point in time where we might want to change that. We might want to grow up as a field, and as the other fields did. So as the car industry did, first they tried to make it work. We are now at that point, computers work. We are quite a good performance. So maybe now we have to find a good trade-off between the security and the performance, and invest more in performance as the car more in security as the car industry and construction industry invested in safety. So that's a good chance right now.
Exactly. So in the end, we underestimated micro-actual attacks for a very long time. Even if we had the basic techniques like flush and reload for many years, and we've seen exploits on crypto, also on SGX and trust zone. And in the end, industry and customers should embrace security mechanisms more and more. Not our mobile phones are faster than the one I got 2 years ago, but it's more safe, and my data is more safe on it. So the entire industry should embrace the same development cycle as we had for cars, where we said we want more safety, and now we want more security on our devices. So from now on, it should be not performance first, but security first, from our standpoint of view.
Okay, so you have heard the story about Meltdown and Spectre now, and some parts of it might be beyond belief. The question now, is it true, or is it completely
Made up.
Garbage.
It's a fact. The story happened like this in the second half of 2017, and we all saw it in the media. Any questions? Thanks for your attention.